What I'm doing tonight is I'm going to go ahead and cover the manufacturing processes number 6, the objective, and that is to demonstrate proficiency of the use of measuring instruments. And as you look at the various skill sets, applied skills, it goes all the way of how do you demonstrate reading, when we look at tolerances, and then proper selection of the tools. And what I'm planning on doing is going through the various lectures of the various measurements by using the different instruments, so on and so forth. And at the very end of this, I've got some pieces here in my office, but I've also got pictures to show you what we measure in our lab and what I'm looking for, so students will actually apply that skill in measurements more than just reading the micrometer, but when and where do you use it, and how do we avoid making errors? And I hit that pretty heavy. So as we're doing that, again, this is going to be the metrology section. I start off my class, and this is my first like 2-hour lecture or whatever, and I said, okay, what's metrology? So I asked them, first of all, how tall am I? And then I'll say, okay, what is my weight? Now, I could probably go to video and show you that, but if, Rob, you can hear me, I think. Are you on mute?
Yeah, I was on mute, yeah.
Okay. I was just going to ask, and if everybody else can hear you, how tall am I?
You are 6 feet. 6 feet tall.
Okay. How much do I weigh? Now, watch out.
Yeah, give me a break, man.
How much do I weigh?
How much do you weigh? 180 pounds.
Okay. Thank you very much. Okay. When I ask them that, before I give them the answer, I say, okay, when I said, how tall am I, what did you first do? And a lot of them will say, well, I compare you to myself, or I compare you to someone else. And I'd say, okay, how much do I weigh? And again, they're doing a comparison. And I said, well, really what you're doing is you're comparing me to something known, or you're comparing me to a standard. I am 6 foot tall and I weigh 206 pounds. Okay? And it's interesting how how they get some similarity in between there, but I want them to start thinking that in order to measure, we must compare to something, and that generally that comparing to something, a measurement, is comparing to a standard. So what is metrology then? So when we look at metrology, metrology is the science of measurement, and measurement is the language of science. And what I hear more than anything, I said, when I asked you how tall I was, you started with a reference point and you went to a measured point. Now, if I start jumping up and down, is that going to help you with that measurement? It's not. So what I try to stress here is that a reference point's got to be fixed. And if that reference point's fixed, then we can get to the measured point. And at this time, I'll raise up my hand and I'll put in, okay, what's the distance between my two hands? And if I keep going left and right, you're not going to be able to measure that. So I hit pretty heavy of that all through all of our measurements, that we need a fixed position in our reference point. With that, what do we measure and how do we communicate? Well, we communicate about size. So in essence, how much do I weigh? It's tall. So we communicate about quality, and I'm going to share a little bit about quality here in a few moments. We indicate about position. And again, when we talk about position, concentricity, parallelism, things like that, hole-to-hole diameter or dimensions. Talk about conditions, surface conditions, and again, we talk about time, in essence, mass, length, and time. So a little bit of history is that way back, the mass was back in 2000 BC, the Egyptian jeweler's balance, and then the length was the Egyptian royal cubit, about 3000 BC, and then, of course, about 200 BC, we got the Greek sundial. So without metrology, there's absolutely no science whatsoever. So in doing that, I want you to think about the good old days. I had an opportunity to see the Aztec pyramids of Mexico City, and I could not believe how large, how flat, how perpendicular everything was. And if you look at it, that's how they measured in those days. And we talk about the yard, which is King Henry's nose out the tip of his finger. Talk about the cubit. We talk about the inch, the hand, the span, and the foot. When I talk about the inch, I said, okay, is that measurement before I hit my thumb or after I hit my thumb? And then I really get in and talk a little bit about thermal heat, how heat in steel will change the size, et cetera, so on and so forth. We'll talk a little bit about that in calibration. So I have a little fun with that. And then I talk about the history of the standard. And again, during the 16th century, it was a combined length of the left feet of the first 16 men to leave church on a certain Sunday. And I thought that was very interesting. The imperial standard yard became the basis for all linear measurements, but it was destroyed in the House of Parliament fire in 1834. And the current standard, the new standard, is in 1855. It's at the British Board of Trade. And that's actually, when I look at that right there, that's actually a test question that I will give them. So you can see a little bit about the history. As I get going then I say, okay, let's talk about what quality is, because we measure this every day. Really what we're talking about, what is quality? And I have some fun with this because I want them to think really what quality is all about, and it's measurement. So we look at quality. These are the different definitions that some people believe what quality is. Like Duran says quality is fit for use. Crosby says, well, it's conformance to requirements. Deming, if you've ever studied Deming, this sounds like Deming, reduction of the variability around the customer's defined targets. Brough says it's a degree of excellence. American Society of Control says it's a systematic approach to the search for excellence. And then Webster's Dictionary says it's an inherent characteristic of something or a degree of grade of excellence. So as I look at that, I asked, okay, what is really quality? So I asked the students, okay, quality is what? What would you tell me quality is? And I'll ask them, I said, when you looked in the mirror this morning, did you see quality? And of course, they'll have fun with that. And of course, one person will say, yeah, I definitely saw quality. I looked in the mirror and say, you're looking good again today. But to have fun with this, I say, okay, to me, quality is Ford. And of course, I get a lot of comments about that. I'm a Ford person, but I definitely get a lot of comments about that. But just to show you that I can do this fair, I say, okay, quality is General Motors. And again, I get some definitions about, or get some fun about that. All right. How about quality is Honda? And of course, being close to Honda here, I get a lot of favorable comments about that. And then I say, okay, how about quality is Dodge? And my son, he just loves his Dodge, but I get, again, some favorable comments about that. And I'm thinking, okay, the only one we can agree on is that quality is Harley Davidson. And I'll have everybody, oh yeah, that's definitely quality. So when we think about quality then, the best definition I ever found is out of Zen and Art of Motorcycle Maintenance magazine. It says quality is neither mind nor matter, but a third entity. It's independent of the two. Even though quality cannot be defined, you know what it is. And I say, whether we go shopping, whether we look at a car, whatever, to us, we perceive what quality is by our own knowledge and maybe our own experience. Well, the problem with that is that quality, we have competition. Ford's competition with Chrysler, Chrysler's competition with General Motors, Honda, et cetera, so on and so forth. And I say the better our ability to measure, the better our ability to manufacture, we can produce quality. And if we don't, we're not going to stay above our competitors. So again, it's competition, and I talked a little bit about salaries there. All right, so when we measure quality, I asked, is 99.99% quality good enough? And I said, some of you, when you're starting this class, you're going to say, okay, I'm going to be 100%, I'm going to do my homework, and I'm going to have excellence. And then something's going to happen, then you're going to say, well, I just want to do what's acceptable. It sounds like some kids. Or how about I just want to do what's adequate? Or how about mediocrity? How about I just want to get by? And every time that it's regression, every time that we start doing that, we get away from really doing the best, that we can, no matter what we do, especially in measurement. So striving to do the best 100% of the time, I could ask, is 99.9% quality good enough? So I'll ask some of the students, especially those working full time, when you look at a quality budget, what do you put in for your budget for poor quality, rework, scrap? And generally, I'll get the answer from anywhere 15 to 25%. So I said, would you be pleased at 99.9% quality in your company? And they said, well, yes. And then I'll say, okay, read that. This is at 99.9% quality. Go ahead and read that. I'll take some time. So you notice I got hanging out on a limb. So really 99.9%, is it really good enough? Well, compared to this statistic, no, it's not. And there's other statistics that you can get out there, but I can't tell you how many times I've landed in O'Hare Airport and 2 plane landings daily is not safe. That bothers me a little bit. And then, so we can see that it really, what quality is continuous improvement. So when we talk about that, we're going to get into measurement then. So what do we measure? When I asked you how tall I was, we measured linear. So that's, lengths, diameters, etc. We measure geometric form. We measure roundness, flatness, straightness, and profile. We measure geometric interrelationships, parallelism, squareness, concentricity, angular dimensions, and again, surface texture. And as we talk about these, you're going to see in a moment, but I lecture on every one of those. But we also measure aesthetics, and it's a psychological response to something of beauty, artistic experience. So I'll say if you saw a brand new Corvette going down the road and you look at that and you're saying, oh man, that is really sharp. That's really some beauty there. Well, that's the aesthetics value. So we measure every day in everything that we do. So why do we measure and how do we communicate that? Or why do we communicate? Well, how about we need measurement to make things? No matter what we do, we need to understand measurement and how do we make things, so we got to make sure that we have the right instrument. We measure to control. And we'll be talking a little bit about that, but again, about control there is if someone is making something for me, I want to make sure that they are within the proper tolerances, etc., so on and so forth, that they are within control. And then we also measure for scientific description or progress. In that lecture, what I end up doing, especially when I talk about scientific description, and I know some of you don't have your mic on, but I'll ask, who was the first U.S. citizen to go in space? And they'll think around, they'll tell me Shepard, or they'll say Armstrong or whatever, and I'm saying, no, who was the first one to go in space? Well, it was actually Shepard. I said, okay, who was the first one to orbit the Earth? And of course, they'll go around. All right, that was John Glenn. And who was the first one to walk on the moon? That was Armstrong. But I said, I want you to go back and I want you to think about Shepard. Here is Shepard sitting on a big firecracker. And you hear the countdown going down, and what do you think he was thinking? And I thought, myself, I'd be thinking, I hope everybody did their job right. I hope they did a quality job and they measure everything the way they were supposed to. Because if they didn't, prior to me, who went up in space? And there were a bunch of monkeys. All right, and they lost several monkeys because of that. And I thought, if we end up doing our job, we're really being successful. If we really know how to communicate and if we really know how to measure. So in so doing, I get into some of the terms then. If I say accurate and precise, what's the difference? How about if I measure versus precision versus how about gauge it? And I've heard several people, let's gauge it. How about if I say standardize, or how about within the ballpark? The issue I have within the ballpark is which ballpark? And then how about 1/10 of an inch? So if I look at 1/10 of an inch, am I looking at 0.1 or am I looking at 0.0001? So again, when we look at that, we need to understand in communication really what we're talking about. So in reference with that, I do go into some of the measurement terms. You know, I talk about each and every one of these. I do this throughout my lecture as far as metrology. You'll see accuracy here in a moment, but amplification, I'll hit calibration here in a moment. I'm going to show you a lab that I do there, and Rob has seen that lab that I do. I talk about drift, the stability of an instrument, you know, the capability to maintain its calibration over a period of time, and linearity, and again, the accuracy of the readings of an instrument over its full working range. The company that I work for, we actually had 60-inch diameter micrometers, 60-inch vernier, and again, what we're looking at, whether I'm looking at 1 inch, 12 inches, 36 inches, is it still calibrated? Is it still accurate? That's what we're talking about, linearity there. So I think everybody can see that. So, and again, I end up having multiple choice questions. Sometimes I'll have a matching question in reference to these. Okay. And again, what's precision? And I'm going to show you some of the lab that I do here in a moment, but that's the degree of which the instrument is repeated measurements of the same standard. I also use the closeness or compactness of the readings, repeated accuracy, resolution, rule of 10. In other words, your instrument or gauge should be 10 times more accurate than the dimension of the tolerances of the part being measured. Sensitivity, the smallest difference in dimension that an instrument can distinguish or detect. There I get into comparison measurement, and we talk about different Dow indicators. And then the speed of response is how rapidly an instrument indicates the measurement, particularly when the number of parts are measured in rapid succession. So that again, there I get into comparison measurement, and you'll see that here in a few moments during some of this lecture. Are there any questions?
Questions?
Yeah, Mark?
No questions. I think I'm. Can you hear me?
Yeah, I can hear you.
Okay. Yeah. No, I'm good. Thank you. I just wanted to give you feedback. Let you know we're out here.
All right. So then I get into allowances, basic size, and again, when we look at allowances, I talk about the mating parts. You know, if we're looking at a clearance or a press fit, you'll see that here later on. I talk about the basic size as far as dimensions, their limits of size, using the tolerances and allowances. Talk about nominal size, and again, that's a dimension that's used for the purpose of general identification. So there I end up using, let's say if I go to a 1/2-13 tap, a 1/2 inch is a nominal size. We'll hit later on, but we'll talk about bilateral and unilateral tolerances. I hit that pretty heavy. Talk about limits, talk about clearance, fit, interference, fit, features, datum planes, in other words, the theoretical exact axis, point, line, or plane. And then mensuration, and which is actually one of my test questions, is the branch of applied geometry that is concerned with finding the area of surfaces, volume of solids, simple data of lines and angles, in essence, dimensional metrology. So again, you'll have a copy of all this. And so dealing with that, then I have, this is the Rob that, Rob's seen this lab, but this is my measurement lab. In here, you can see back in the left corner, a coordinate measuring machine. To my right is our instrument cabinets. And then as I look at this, I have the groups come in. And what they are to do is saying, okay, I want to measure the length, the width, and the height of this room. So as they look at that, that's what I want done. Okay, it's very simple, simplistic. You know, they all know how to measure. And I said, okay, now there's your instruments. You have a yardstick, you have a plastic ruler, you have a 12-inch ruler, you have a 6-inch ruler, Starrett, and you also have a Lufkin tape measure. So as they're doing that, is I'll split them up, and I'm saying, okay, usually if there's someone in a class that I'm pretty sure has never done very much measurement, I'll have them the opportunity, okay, which one were you going to pick first? So as you're looking at that, knowing the assignment is going to be to measure my room, the width, the length, and the height of the room, everybody that I know, I would say, okay, I want that tape measure. So we go with that. So then someone will pick the tape measure, and next somebody will pick the yardstick, and then they may, I think I actually have another 18-inch that I use also. But I'll use different instruments, if you will, or measuring instruments. And again, what they are going to do is measure the room. Now, I'll tell them that there's going to be a time limit. And usually, you know, I'll say 10 minutes or so, and I don't hold them to that. But what I'm watching, if you go back and you think about measuring this room, how are we going to make mistakes? Well, if you're taking that 6-inch rule, you got to overlap that thing. So in other words, you got to count how many times you overlap it, or you mark it, and you go to the next one and mark it, next one and mark it. I actually have people that will literally count the blocks, and they'll measure the blocks. So how do we make mistakes there? How about computational mistakes? There are math mistakes, etc. The other area that we'll get in trouble, they don't measure to see if the room is parallel or square, perpendicular. So again, you know, I'm trying to show them is how do we make mistakes in measurement. And I have some fun with this. So as you look at it then, and they come up with their measurement, I'll have each group put it up on the board what their measurements are in feet and inches. And you're going to get some diversity. Quite a bit of diversity. I forgot to share with you, but I do have an electronic instrument that I can actually use that I can put up against the wall and hit it, and it will give me a digital readout of what that measurement is. Of course, that's more advanced, but I don't allow them to use that. All right, so, okay, they get the measurements, and they're saying, oh, my goodness, we must be off. Look at that tape measure. Well, I'm saying, okay, now how do you know the tape measure is correct? Because if you look at it and look at the room, all right, how do we make mistakes in measurement then? Well, you know, the accuracy of measurement is only going to be as great as that of the standard. Accuracy is diminished by errors. And again, I hit calibration here. Calibration is a comparison to a higher standard or the test of accuracy. And again, repeatability is usual test for precision. So I'll ask them several times, how about remeasuring it again? And every measurement alters the object being measured in the measuring system. And with that, what we need to do is eliminate the separate measurement acts, or the different parts, or the fluctuating conditions, or the position variables. So as I discuss that, I'm saying, okay, how many of you had trouble trying to find a straight line? You had to move around something, or you really couldn't go from one corner to another corner without something being in the way. Well, and again, we're talking about looking at these errors. And we also talk about the least positional error results in the line of measurement, or that standard, or that axis of comparison are all in line. So they're starting to get a little bit of knowledge here, or skill set, in measurement. So as you see that, and I'm sure that we've all done this, we've all had some issues, is, okay, let's look at that tape measure. And if you look at the tape measure, what do you see? If you notice, it's not starting at 0. I cut 1 inch off of it. So every time they use this, they're 1 inch off, and they don't catch it. And I'm saying, okay, what's the problem? What's the root cause of your measurement being wrong? And they'll say, we didn't check the accuracy. And I'm saying, how about you didn't check the calibration? All right. And they don't forget it. I'll tell them from now on, no matter what instrument we use in this lab, either you check the calibration, and as I lecture, I talk about calibration pretty heavy, whether it's an outside micrometer, a depth micrometer, vernier caliper, et cetera, so on and so forth, Johanneson blocks, gauge blocks. I show them how to check calibration. And like for a 6-inch scale, they may ask me, is this calibrated? And again, of course, I'll tell them yes. So I have a lot of fun with that, and they don't forget it. So again, calibration is a comparison to the higher standard is the test for accuracy, and they just don't forget it. So how do we make mistakes then? Well, we make mistakes by using not really good quality instruments, or we call it the tool or inherent instrument error. We go back, if you recall, I did have the stare, and I also had a plastic ruler. So when we look at quality instruments, we can make mistakes, have errors because we don't use a quality instrument. We can make mistakes by observational error or the eye. And later on, we'll talk a little bit more about this, but when we talk about parallax error, reading a vernier caliper, we have an issue with parallax error. And what I try to use is, you think of a car speedometer to the passenger. If you look at a car speedometer and it's straight up, I'm doing 60 miles per hour, but my passenger looks at it, he's not going to see the 60. So again, that's what we call the parallax error. We can have manipulative error, or the hand, and that's cramping. So if you recall that, so if I hold my hand up and I want you to measure something that's pretty heavy, and I'm moving, all right, that's manipulative error. So again, we're not staying fixed in our reference point. We consciously make mistakes in measurement because of a bias. And I will show you a little bit about that, what I do in my lab here. We talk about bias mistakes, but we end up making bias mistakes. And there I'll say something like, how many of you went through a stop sign not realizing that you stopped or not? And of course, they'll all say something, well, maybe I've done that or whatever. Okay? And then, of course, as I just added poor calibration or lack of. And again, that's process assessment. So when I teach the class, I'm trying to show them these are the things that we need to minimize. And if we have an issue with any of these, then we're not going to have reliable measurement. So we need to diminish these errors. So then I talk, okay, what's accuracy, precision, reliability? Again, as in the classroom, I'll say, okay, what's accurate, what's precision, what's reliability? So in so doing that, I'll say, okay, I'm going to use the target analogy. You're looking at someone that's going to be shooting at a target, and we're going to see which one's accurate, which one's precise, which one's reliable. So let's look at the analogy for the shooter. We're looking at the skill of the shooter. It could be the variables of the ammunition, variables in the rifle, variables in the environment, again, wind, glare, and distractions. Man, have trouble today because it's pretty windy outside today. And then the target's going to verify the results. When you look at the equivalent of the measurement, then that's up to the skill of the observer, variables in the instrument, variables in the setup, variables in the environment, and again, temperature, dust, distractions. And again, the calibration will verify the results. So let's see what happens here. Let's go, okay, we got 5 men. And we can see man A has 5, man B has 0, man C has 10, man D has 10, man E has 10. So I'll ask them, okay, who's accurate? And they'll say, it looks like he's more accurate than anyone. Okay. And why do you say that? Well, it's in the middle. Okay, but I'll say, okay, let's define accuracy. And accuracy is anything within the target. So if I would say, I will give $1,000 for every one you hit within the bullseye, C would get how much money, D would get how much money, E would get how much money. So they're all tied. It doesn't matter if it's close to the line, but it's within the target. So then I talk a little bit about within the tolerance then. So if it's within the tolerance or within the target, it's accurate. So then I'll say, okay, which one's more precise? And again, they'll look at it and they start thinking a little bit, and they'll say, well, B's precise and D's precise. And again, D is really precise. It's the closeness, compactness of the readings. But who's reliable? And they'll say, first, well, B's definitely not reliable. But it looks like E again is reliable. And I'm saying, okay, what about D? Okay, what about B? Why isn't B reliable? Because he is. And they're saying, no, he's not. I said, yes, he is. Reliability. It's repeatability. So he's reliably bad. All right. So I had a little bit of fun with that. I talked about the accuracy, the precision, the reliability compared. And then I'm saying, okay, let's change something here. All right. We have the wind. Let's see what the wind does to it. So now we look at the difference. Who's accurate? And again, they'll say he's accurate. Very good. Who's precise? And again, they'll look at, well, they don't really want to say D, but they will, because it's the closest compactness of the readings. Definitely A is not, doesn't have the precision that the others have, and C doesn't either, really. So again, then I'll say, okay, who's reliable? And again, they'll say E's reliable, and again, B's reliable. And that's what I want them to pick up. And now I'm going to change the tolerance. Oh, wow. So now here again. So we change the tolerance. Again, it's tighter, if you will. Who's accurate? I reduce the size by 1/2. And they'll see it. And they'll saying, okay, it looks like E's accurate. And I go, very good. Who's precise? And again, they may say B, and again, they may say D, and again, they may say E, and that's okay. They're not going to say C or A. And then I'm saying, okay, he's reliable. And again, B and E. So I want them to start thinking truly in that definition, using this analogy, this target analogy. When we talk about accuracy, we talk about precision, when we talk about reliability, what's optimum performance? So then I talk about, well, okay, accuracy is an adherence to prescribed standard. And again, adherence is to stay firm in supporting or approving, sticking fast, staying attached to, prescribed in order to advise the standard is agreed upon the unit of measurement. Precision is the fineness of the readings, dispersion of the measurements. I like to use compactness. And again, the fineness, the clear, the sharp, very thin, the small. Dispersion is how much is it broke up. And then reliability is the probability of achieving the desired results. And that's the likelihood so they occur. So you're starting to thinking now in measurement, truly what accuracy is, what's precision, what's reliability. And again, I think that helps by showing the target analogy, because I know a lot of people say, I always thought precision meant accuracy, and no, it does not. Optimum performance, as we look at it, is to have everything within the target, precise, and reliable in the target. So again, we end up talking about that, and I think it helps have that. Any questions over that? And again, I have quite a bit of fun with that. Okay, so then we already talked about inspection procedures. And I talked about the different inspection. We talked about first piece inspection, what's that consist of. And I generally say, well, generally first piece inspection, you're running a CNC machine, you're running 100 parts. We're going to check that first piece to make sure the program's correct. Talk about sampling plans, roving inspector. And again, when we're looking at that, the inspector just he go to various lines, various machines, et cetera, so on and so forth, and he produces a sample. Again, when we're looking at that, I'll say Dannon Yogurt. They will have a roving inspector, and he's got a little ladle, and he'll reach in there, and he'll test the ingredients, et cetera, so on and so forth, what's in the yogurt at various stages. And then a batch, let's say, for example, we're going to take 10 out of 100. Every time that we start looking at something, we're going to take 10 out of 100, and then I'll say, okay, final 100% inspection, we are going to measure everything 100%. And I'll say, okay, as you look at that, which one do you think is really going to give us quality? All right, and of course they'll say, well, the final 100% inspection is going to do that. Because first piece, so you could have an error in the second piece. Sampling plans, you got open-ended, and then batch sampling, you got open-ended. I said, okay, final 100% inspection. All right, so as we're looking at that, okay, what do you see there? Okay, and now we're talking about perception. How many can see the young woman, or how many can see the old woman? And again, if you look at that picture, and I've got quite a few of these, but I'm not going to share a couple of them with you today. But as you look at that, I hope you see them both, but if you don't, this is the nose of the elderly woman. There's her mouth. And then the young woman, this is her hair, that's her eyelid, that's her nose, and then that's her chin. And that's her ear. So I hope everybody can see that. All right, and again, sometimes they don't see both of them. I'll ask them, okay, when you look at perception, that dot, is it closer to the top or is it closer to the bottom? And again, they'll say, well, it's closer to the top, but then I'll take a measurement. Usually I have a 12-inch rule, and I'll measure from here to here, and I'll measure from here to here. They're exactly the same. So again, I want to start thinking about perception is not always correct, and we make mistakes in metrology because we perceive something. All right, I'm going to give you a test. I'm going to let you down. What you're going to do is I hope everybody has a piece of paper. You're going to write down what you read, okay? Write down what you read. Here we go. I hope everybody's got a piece of paper. Give you a moment. And again, you're going to see something. I want you to write down what you read. Here we go. Go ahead, write it down. Okay, give me another one. One more. Okay, again, we're talking about perception. I ask you to write down what you read. Well, let's see what you got. First one said, once in a lifetime. And I'll probably have about 90% of the students will miss that because they didn't read it. All right? Their mind, their perception, what they perceived it thought it was going to be. So again, they're going to miss it. The second one, they may get it now, but a bird in the hand. So again, some of the students may have caught it, but you may have some that they're just going to miss it. And then, of course, the last one, the rain in Spain. So I'm showing you how we make mistakes in perception, or the bias mistake. Okay, this is another one that I do, and I'm going to give you a little bit of time to do this, is I'll pass this out, and of course you just got the screen, but what you're going to do is I want you to count in the box how many times the letter F appears. Okay, how many times the letter F appears. So there it is. I'm going to give it a little bit of time. You're going to do 100% inspection here. How many times does the letter F appear? 100% inspection. Okay. Everybody's got a number. What is that number? And I'll put the numbers up on the board. I'll get anywhere from 8. I'll get 17. I may get 18 or whatever. I may get 12. I'll get a lot of different numbers. So what I'll have them do is I say, okay, put your total right there. Now what I'd like for you to do is whatever number you had is I want you to read it backwards. Go this way. Go right to the left and see if you can get the same number of how many times the letter F appears. Okay, generally what happens, I hope you're finished, but generally what happens is people will improve. And sometimes I'll have people get it exactly right. The reason why I do it this way is I'm saying, okay, when I ask you to count the letter, how many times the letter F appeared, generally what happens is like you read it. You go left to right, and you go down. Well, let's do something different. Let's go right to left, and let's go up. And by doing that, generally, we may be more accurate. So how many do we actually have? Okay, well, we have 5 in the first row. 3 in the second row. 2 in the third. 2 in the fourth. 2 in the fifth. 0, 1, 1, 1, 3, 1, 0, for a total of 21. Okay? And again, we have some fun with this. I say, okay, what would you do different? I give you $10 for every one you found, as long as you got them all right. And again, they'll say, well, I would cover them up or whatever. Generally, where they make their mistake is that when we go to of, they won't catch it. And there's another of here. They just, whatever reason, they do not catch the of. So again, I show them at that time, 100% inspection is not always the most accurate that we can do. It's really your procedure, your process. So in so doing, and again, I asked, okay, which one of the upper lines does the line at the right connect? And again, they'll say the bottom one, but if you take a straight edge, you go across here, it's actually the top one. How many black dots do I have? And again, I don't have any. All right. So now we're going to get into measurement. I have a little bit of fun. Again, that's more of an introduction. So we talk about measurement. We talk about gauges and tolerances. So we already talked about nominal size. We talked about a dimension. Again, what is size, what's allowance, and what is tolerance. And again, tolerance is the total permissible variation of the size, and it's a limit of size. So I will get up on the board, and I may say like 12,250 plus or minus 3. I'll say, okay, what's my tolerance? What's my limit? what's my high limit, what's my low limit, and again, we'll be talking in a moment about what's bilateral or unilateral tolerance. Again, a basic size, and I get a little bit into GD and T when I talk about maximum material limit and minimum material limit. So I talk about, maximum material limit is the limit of size that provides a maximum amount of material for the part. So if I give them a 12-inch rod, give them a tolerance of 12 inches plus 10 minus nothing, so then the maximum material limit is 12 inches, 0.010. And then the minimum material condition is which one would give you the least amount. And again, where they have an issue with that is I give them an ID. And they have some issues with that. So talk a little bit about GD and T there. I like to use, when I talk about limit of size, I like to use maybe a goalpost. If it's outside that limit, does it count? No, it does not. Again, there's your tolerance limit, and there's my unilateral, bilateral tolerance. I put several up on the board. I'll tell them, again, the unilateral tolerance is a variation in one direction. Doesn't matter if I go high, doesn't matter if I go low. It's only in one direction from the nominal size. And then bilateral tolerance is both directions. Then we talk about fit, tightness, clearance, transition, interference. And I may have parts that I can show them where I have clearance, where I have interference, etc. And then that's the difference between the fits. The clearance fit, interference fit, transition fit. Okay. And then, again, when we look at these manufacturing machine parts, according to the methods, again, we're looking at the minimum dimensions established. More important, members of whatsoever machine or mechanism is to be constructed, and then we have limiting dimensions for purposes to prevent both unnecessary accuracy and excessive inaccuracies. And a certain degree of accuracy is essential for proper functioning of the assembled parts of the mechanism. And then proper limiting dimension promotes efficiency in the manufacturing, and then ensures the standards of accuracy and quality that are consistent with the functions of different parts of the mechanical device. Okay, the other thing I try to hit really heavy here is the interchangeability. In other words, if they're made within the specified limits, they're considered interchangeable or capable of use without selection, but there are several degrees of interchangeability. And again, what we're talking about, are we looking at the same model? A certain model may fit. I talk about a little bit about aftermarket here, that sometimes it may not fit because it's not exactly per the standard, if you will, or per the print, accurate per the print. Sometimes you may have to do something with it. Selective assembly is sometimes termed interchangeability, but it also involves the selection or sorting of parts. And again, it's desirable that if we don't have to touch anything when we end up buying it, as they said, it's noted that strict definition of interchangeability does not imply that the parts must always be assembled without handwork. And then we'll go around the class and I'll say, have any of you ever bought anything that you had to take it home, you had to do an engineering change with it, file it down, rebore the hole or whatever to get something to fit, or you just flat send it back? And sometimes, yeah, we have to fit them, and it may be because of that design process. Okay. So when we talk about limit and tolerance and allowance, where we get to have an issue then, it's often used interchangeable, but they actually have distinct meanings. And again, the tolerance is the two limits or limiting dimension of given a part, but the allowance is the difference between the limiting dimensions and the mating part. And what I end up showing here is that we could actually have an issue if our tolerance isn't correct. So I could have a ID of minus and then an OD of plus and be within the tolerance, and it may not fit, especially if I want clearance. And that's what I share with them here. All right, the difference between limit and tolerance and allowance. So they're getting some conceptual idea of when do we use each term. Okay, a little more detail. And again, the basic size of a dimension. We look at the dimensions, and I'll say, okay, we're looking at that stud, 1.248 plus nothing minus 5. Is that bilateral or unilateral? So you can see the tolerance of half on each side. Another one, terms maximum and minimum interference. So again, they'll look at that and they draw it out and they'll see the interference that's permissible. The way we have the tolerances. And their basic size then shows the maximum limit for both the ID and the OD. Okay, illustration showing the terms of maximum and minimum clearance. And I may ask them, okay, how much clearance can I have max or min? Again, they got to look at the tolerances to come up with that. And then I talk about dimensioning. And again, the incorrect method of dimensioning, because we have different tolerances here. I have a tolerance here, I have a tolerance here, and I have a tolerance here, and we can't hold all of them. And sometimes we get in trouble because of doing that. So in other words, if I hold that, I hold that. Could that be wrong? And it could be, whatever. So again, that's not really a correct way. And again, we're showing the same thing here. Looking at the dimensions. So what do we need to do? How about open tolerance? So in other words, we've got a tolerance here and we've got a tolerance overall. And or the correct dimensioning on all the parts. Okay. Then on the board, I'll show them, okay, sometimes we have a trouble with stacked up tolerances. So on a print, I may have 1 inch plus or minus 1/64th typical. Typical means, okay, in between that, I don't know why that square is there, but in between all those lines, all right, I can have 1 inch, either plus or minus 1/64th of an inch in between all those holes. So in other words, each separation between center line and center line, I could have that 1 inch or the 64th tolerance. If I'll say, okay, everything's plus a 64th. So by the time we get all the way out here, we're looking at 1, 2, 3, 4, 5, 6, 7, 8, 9 64ths, that literally this hole could be off from where it's supposed to be. And that's because of the way that we've got it stacked up. I mean, the print shows that, we're okay. And I'll say, okay, will the mating part fit? Well, what happens if the mating part is minus? Well, that's not going to fit. I mean, it doesn't matter if it's right on. It's not going to fit because literally we could be 9/64ths off on that last hole. So I'll say, okay, what can we do to correct that? And I'll say, whoop, let me go back. All right. What I'll say is, okay, let's go ahead and hold it from a reference data plane. So in other words, that hole, and then the next hole, and then the next hole. So everything's coming off of this datum plane. So as I do that, and I show that, and again, I mark this up on the board, I'll say, okay, last hole, how far can it be off from the center point? And they'll look at it and they'll say, the most it can be off is the 64th of an inch, plus or minus 64th of an inch. That's exactly right. So every one of those holes, the max it can be off is the 64th of an inch because I don't give it an opportunity to stack it up. Don't quite see that mistake on CNC, but in the old days when we used to lay out and spec, we did. Okay, are there any questions on the tolerances or fits? Or I could say, what questions do you have?
I'm good here. You're doing the same thing I'm doing.
Good.
So.
All right, so now we're going to start measurement then. What they all saying, all that introduction, all that stuff, first thing we do, besides already use the tape measure, we're going to measure with graduated scales and scaled instruments. So in so doing, what we'll end up talking about, I'll talk a little bit about inspection and layout. And then I use the examination of, let's say, I'm sure we've all done this, but we've cut something out of a piece of paper, or a piece of wood, or whatever. We have a layout, a reference line, and for instance, if I have a casting edge. And I'll talk a little bit about machining here. I'll talk about, we may machine to this line here, that's for reference only. And then when we put it up on the machine, we'll turn it around and indicate across that finished dimension to hold the other dimension. We would not machine it to the reference line. It wouldn't hold the tolerance that we normally would like to have, especially if we're looking at plus or minus 1 or 0.02 of an inch. So it does refer to describing the lines to show the limits of the various machine operations. Again, as I said, for precise parts, layout furnishes a guide, but the precision of the tool and the operator determines the actual dimensions. So they may machine one side, turn it over, and line it up, then machine the other side. Okay, so when we look at the scaled instruments then, we talked quite a bit about you're going to see this in a moment, but we'll talk about a combination set, combination square. We're going to talk about the calipers and vernier scales. And again, I hit quite a bit about the reference point. You should consider the following factors when using a steel rule. That number one, what steel rule are you going to use? And I have various ones that I will show. I'll have a hook scale, a smaller one, 12-inch rule. I can actually have a 72-inch Starrett that I borrow from the company I used to work for. And then what method of holding the rule apart allows us to obtain more precise and accurate measurements. In this conversation, I really talked about, and it's one of the requirements for them to take this class is they have to have a 6-inch Starrett rule, and they can buy them in the bookstore. And with that, I'll say, okay, what's this really used for? You know, and I'm hoping they're saying, well, we use it to measure scale dimensions, you know, within a 64th, an 8th, 16th, and 32nd. And I'm saying, yeah, but how many have used this for a screwdriver? And I also say, well, I used to have a gentleman at the company I worked for, he would use it to spread his peanut butter. Lick it, put it back in his pocket. It's not what it's for. Okay, and again, it's used to do measurement and to be precise with that measurement. So we need to look at what's the best relationship as far as the reference point to the measure point, the graduations on a rule. So in so doing, I give them a rule reading exercise as they're looking at it. Then I give them the answers. I did this several times. Actually, on one of my exams, they'll see something like this again, where they have to come up and give me the right answer. So it just assures me they know how to read a 6-inch rule. Just let you know, in my tolerances, my scale dimensions are plus or minus 1/64th, and my precision measuring instruments are plus or minus 1,007 inch. And then later on, we'll talk about degrees, but I allow plus or minus 15 minutes. It's interesting, because sometimes I'll get students that's really never done much measurement at all using a 6-inch rule. Okay, so how do I read it? And again, it says you should read the scale of the rule to the instrument to the nearest graduation. Number one, why? To interpolate between the graduations, you compromise reliability of the measurement. And then it talks about there usually is a rule nearby with sufficient discriminations for the job. So you check the finer scale when you need to, you know, especially if it's in between. If I give you a tolerance of plus or minus 1/8 of an inch, you don't need to look at the 32nd. So you use define a dimension that is needed to be reached, or the finest scale that will be reached. So again, we look at discrimination and precision. So whether we're looking at a 0.02 scale, a 16th scale, 32nd scale, or 64th scale, how should you read it? In other words, really having the proper discrimination that we need to use to check it. So that's just the finest precision. All right, then I get into depth gauges, where we say we use these to transfer inaccessible reference or measure points to accessible ones. And then again, some depth gauges, like this one here, they do have a scale for 30, 45, or 60 degree angles. But it has limitations. You're limited to the width of the head. That can be spanned. And then the wear at the end of the blade. We talk about that. And I talk about the advantages and disadvantages of holding it properly. So, and again, we're looking at, are we really down to our measure point, our reference point? And if I'm using a hook, am I really there where I'm supposed to be? So you're transferring the measurement to the rule itself, the equivalent point, reference point, measure point. And here I'll share also, I said, here's sometimes we got to watch out for. Let's say for instance, that we're supposed to have a flat bottom hole, and we got a little bit of radius here. Are we supposed to have this dimension all the way down flat on this side, or is it supposed to be at the bottom of the hole? That needs to be defined as far as your reference point. Combination set. Talk about the main components, the center head, the protractor head, the square head, the blade, and what sizes are available and expressed by the length of the head. And again, the heads can either be planed or hardened. Again, you can order those that way. And then you have clamp locks. So in other words, to lock it in a position, that's a clamp lock here, a clamp lock here, a clamp lock here. And then, of course, you have the level that's on there. In so doing, the proper use, and again, why do we use a combination set? Combination square. Well, again, it eliminates this, the eyeball, which really has very poor reliability. Or how about a reference block? But again, if we can go ahead and end up using the combination square, we're going to be generally more reliable. We can add attachments. So again, sometimes, and I try to share them, every time that we start adding an attachment, we have a possibility of an error, but this was okay because it's fixed. It's got to be, make sure it's against the top. Make sure the surface is flat, because it may not be square. And again, the part itself may not be square. Some more uses. Here I share with them, you definitely want to watch overhang, springboard effect, especially when you start using a dial indicator out there. And watch your force. And again, coming down. And again, I'm showing, okay, to make sure you don't measure the top of the radius, that you're down here actually to your point, your reference point, which is fixed. And again, it's important to measure or gauge to minimize overhang. Protractor head. We talk about what precision we can use. Finest precision is 1 degree. Center head. Also share with this a little bit. Sometimes I'm sure we've all done measurement, but we'll hold this at 1 inch. And then we'll measure out here. And if it reads 6 inches, we'll say it's 6 inches. We forgot about the 1 inch right here. And again, it's a bias mistake. I've done that. Drill a hole 1 inch long. Don't tell my wife I did it on brand new hanging lights on a garage. So it was covered up. I just caulked it. So again, shows the proper way to use it. And again, the center head versus trying to do whatever. But again, what we can do is try to find the center of a round part. Maybe we want to center drill it, etc. And again, when you read it, and I share with them, you want to make sure what you're reading. You know, are you going left to right, right to left, etc., so on and so forth. And I end up having, when I use my 6-inch rule, or 12 inches, I'll have a bar going across. And it could start at 3 1/4 and go up to 4 1/2, and they got to tell me what that measurement is. They better not tell me 4 1/2, or they'll miss it. So make sure you know what you're reading. All right, so when we look at reliable measurement, these are just to have reliability. And again, you know, observe all precautions for using the steel rules. You don't spread peanut butter with it. Assure that the heads are not worn excessively. And be sure the line of measurement is parallel to the blade. Watch out for your force as far as the measurement. And then be sure the scale is read in the proper direction, which I've already said. For work from a plate, be sure the blade is in contact with the plate itself, surface plate, for example. Watch out for that parallax error. Make sure all your attachments for wear and squareness are correct. And I really hit that on about everything that we do, especially when we start using a dial indicator. And make sure the overhang is as short as possible. Okay, before I get started, are there any questions on the steel rules?
I don't have a question, but I will make a comment.
Yes.
I don't know if you see it at your level, but at my level, typically we go over this when they're freshmen in high school.
Uh-huh.
And I'm still amazed at how they cannot read the scales.
Oh, yeah.
It drives them crazy to go from a steel ruler that's divided out into 8, 16ths, and 32nds of inches. They just, like I said, it blows my mind how they just can't read scales.
Yeah. The other thing that blows my mind is they don't know how to add.
Yeah.
My stepdaughter teaches for the first year this year. She graduated from Bowling Green. She's teaching 5th grade math. And she'll come home and she says, I can't believe these kids don't know how to add fractions. You know, and they were supposed to have that in the 3rd and 4th grade, and she's doing the 5th grade. And I tell you, I get college kids that will come in here, and they really don't know how to do it. And we actually have a math class where we actually have to start teaching that again.
Well, see, my students are afforded the opportunity to take some online courses with Sinclair Community College.
Okay.
And calculus students get very upset with me when I make them take the lower math classes.
Okay.
But at the same time, I can turn around and give them a test on fractions, and they'll fail it because they haven't used it in so long.
Right.
They just they actually get so high. Coming down and doing basic stuff drives them crazier, and they get so used to their computers. If another one asks me for a digital scale, I'm going to smack them. It always amazes me how they have trouble reading the scale, even after they start to learn how to use the thing. And I will also confess I have many projects at my house that are off by an inch also.
Okay, good. Well, I did that one. I definitely drilled a hole 1 inch off.
And I measured it 3 times to make sure it was right.
Yeah, I did. Yeah. And then you remeasure it and want to know what went on. It doesn't fit. Okay. Get into calipers then. And what I share here is more when we talk about direct and indirect measurement. And again, this would be an indirect measurement. So in other words, I can measure something unless I'm comparing. If I actually want that measurement, I have to have a standard to confirm it with. So we look at a reference point and measured point and different types of calipers. And I bring all these out. I have various sizes, so on and so forth. We have the firm joint, the spring joint. In other words, firm joint, and then we have the spring joint. We talk about dividers, outside calipers, hermaphrodite calipers, inside calipers. Again, when we use those. And then we talk about general help. When we look at a spring caliper, and again, has no scale. And again, we can look at inside or outside, and I will show them how we transfer the measurement. So in other words, if I'm looking at here, it's an indirect until I come direct as far as outside. And then we can look at inside. And what we're starting here is when we talk about feel and spring, et cetera, so on and so forth. Now, actually, when we talk about scale, we talk about these calipers, one of the first parts that they measure, this is what they have to use. They have to use inside, outside calipers and a 6-inch rule. I want them to start understanding, first of all, how to measure with the calipers, get the proper feel. In other words, you don't get the spring, et cetera, so on and so forth. But how do you transpose the measurement? So we really start getting into doing some measurement. All right, so we look at dividers. You know, the advantages of a divider, reference point to the measured point. And I share with them this. I said, how many remember having a compass in school? We drew circles. And again, show them the more examples, dividers, outside calipers, inside calipers, hermaphrodite calipers. When I give them my final exam, which you'll see later, but I'll show them a picture of an instrument and they're supposed to identify it. I really get a lot of different spelling on hermaphrodite. Transfer measurement. And again, scribing arts remains the chief use of the dividers. You know, you transfer the dimension from a scale, for the measurement, one part to another. And again, or to lay out a line, et cetera, so on and so forth. I also share with them how to do coordinates on circles here. Whether I want 6 or whatever, we use the machinist handbook to come up with what we call the chord. And again, the advantages of the dividers. Manipulative convenience. And again, they can save time, as I said, without decreasing reliability. And I talk about line of measurement quite a bit. And so we're going to start getting involved with this, especially when we use precision measuring instruments, but you might as well get used to it right now. I said if you can use a shoulder, and again, it's really reliable to do that. Trying to go the correct line of measurement. It's basically perpendicular to the part. Reliability, and again, if we're checking comparison, then it's most reliable. Less reliable is using a precision measuring instrument that's inside micrometer. And again, the least reliable is using the scale. But if I give them a tolerance of plus or minus 1/64th of an inch, I would still want them to get used to it. There are times when you have to do this, especially in the industry. Checking a slot, et cetera, so on and so forth, diameter. And we do all three. rock over technique. Starting to get used to the feel. And again, precision depends on your feel. You're getting used to it right now. Starting to. And there's my good old hermaphrodite when I use them, or how to use them. And a good old surface gauge. Whether I'm transferring a line of measurement to a part, or I'm going from the edge, my reference point, these have pins that come down, and I show them how to do that. And then to use a scribe and coming through here, I'm drawing a line measurement that's parallel to my reference point. Measured point, reference point. Again, they have gauge pins that comes down that will push those down in there to run parallel against the edge. All right, how about micrometers then? That was all scale dimensions. Now we're going to be getting into precision measuring instruments. We talk about outside micrometers. I show them various sizes micrometers. And again, I can go to work, and we actually have a 72-inch outside micrometer. The company I used to work for, I actually ran an engine lathe that would do 60-inch diameter. And I'd show them that. And sometimes I'll actually take them to the plant so they can see the machines. When we talk about the outside micrometer is designated by its largest opening, not its range. So in other words, all those mics have a 1-inch range. And we talk about amplification of the screw. In other words, each turn is so many thousandths of an inch. I show them that here, the reference point. We have a reference point, a measure point. So lateral movement of the scale coming in. And then we talk about the various parts of a micrometer. I'll hit the anvil, the spindle, the opening, the frame. I'll talk a little bit about, some mics have ratchet stops on them and what they're used for. Talk about the thimble scale, the barrel scale. And again, the clamp ring, sometimes there's a lever. I have actually both that I can show them, but there's a lever that will go up and down to lock those in. And then we talk about the actual measurement itself. Measure point, the reference point, line of measurement. Okay, and then we actually get into reading the micrometers. And what I'll end up doing is we'll cover this brief lecture of how to read a micrometer, both metric and imperial English. And we'll talk about, okay, let's look at it. Look at the sleeve, we look at the thimble, the anvil, etc., so on and so forth. We'll talk about it, and I'll explain to the graduations and whatever. Then we actually get into, all right, what's the first graduation? Second, third, fourth. As I said, going up the for my measurement, and then I'll say, okay, what's this dimension? 200 thousandths of an inch. $225, $250, $275, and 300. So they're starting to understand a little bit how to read them. And I'd say probably, 75, 80% of the students really don't know how to read a micrometer unless they've been in industry before. So then I talk about, okay, let's get into the finer precision with a thimble. So we talk about how to read that. And at this time, everybody has an outside micrometer. They're looking at it. And I'll say, okay, let's set the micrometer. Let's go ahead and read this. 385. .326. And boy, we have some problems with this one though. When I tell them I want to go, okay, I want to go to 10th graduation, 0.001. And we actually have micrometers that have these graduations on them. I show them how to do that, how to read that up. This is when we actually get into the parallax error. Show them how to read it. Okay, and then I actually have enough that I can show them without the vernier first how to read it. And what I'll end up doing is I have pin diameters. I know what they are. And I'll have them go around the room with maybe 6 different diameters. Everybody has to mic them and write down their dimensions. We'll see how close they are. They actually are. I'll have some students get right on. Some students will mic it too tight or too loose. Generally, like I said, I'll give them a tolerance of ±1. That's what we're trying to achieve, especially when you start doing their lab measurement. And again, we'll look at this. I have various exercises that will end up doing something like this. They're supposed to give me the dimension, reading the vernier scale. I actually have one of these, the old Brown and Sharp. It's hard to read sometimes, how you can make mistakes. And also to show them how we can make mistakes here, that this is 249, not 274. Again, they end up making that mistake sometimes. While I'm thinking about it, I do not allow digital. I don't allow electronic digital on anything. They have to do it the good old conventional way. And of course, I hear somebody say, well, I have a Dow vernier in my office, and what I use all the time. That's good. You're going to learn how to read a vernier. Proper way, what we can use it for as far as external points, external lines, external parallel lines, combination, but we can't do some of that inside. And this is where I bring it out. I actually have ball attachments that I will show them how to use that, put a ball here and a ball here. But with that, you got to make sure that you take your diameter of your ball away from your measurement. And again, we're looking at the measure line to the reference line. I have fun with this one too. I show them the proper way to hold a micrometer. And as you're looking at here, you don't just wing it with your hand. And I actually have an old 2 to 3 mic that I have out there, and I'll wing it and I'll let it go and I'll hit the floor. And that's when I talk about, I said, if you ever drop an instrument in here, first thing you do is you check for damage. You check the anvil, the spindle, etc., so on and so forth. And then also you check calibration. You just don't put it back in the box and put it in the cabinet and like nothing's happened. And again, I have an issue with that sometimes. I'll take a picture of a vernier later that someone actually was using it on a machine and cut the jaw off and put it back in the box. Vernier caliper. So again, I watch them how they measure. They'll pick the pin up or they'll try to hold it and leave it there and try to use the edge or whatever. It's interesting to see how they try to get the measurements. Tell them what the ratchet stop's for. Again, a rock over technique. they get a lot of practice prior to their exam, as far as lab exam. And we talk about standards. How do we check a micrometer? You know, off to one, we can go to the anvil and spindle, and we can get a 1-inch rod, half-inch rod, or whatever. We talk about the standard then. Again, another picture. The other thing that I do, and I just thought this, but Starrett has a tool measurement little handbook that you can get free. And I'll try to get them, and I'll get that, so I'll pass them out, and through that handbook, it will tell them how to read a micrometer or a vernier caliper. I will also give them a catalog. And the reason why I like the catalog, because we don't have all the instruments, like, for instance, the scale, the hook scales, et cetera, so on and so forth. But they can look through there and look at all the various instruments that we have out in industry today. And Starrett's pretty good at that. If you ever go to a tool show or whatever, you can usually ask for them and they'll mail them in to you. They like to get the Starrett name out there. Go to inside micrometers. And again, we talk about the various sizes, measured point, reference point, how to read them. Watch out, as far as geometry, what you're looking for. And again, the inside, we have these out in the lab, especially if you're using this type here. In other words, you got the half-inch spacer that goes in between there. And again, if you're using that spacer, you want to make sure that if it's there, it only has 500 thousandths travel. So if I have a half-inch spacer, I need to add that 500 thousandths to whatever my reading is. I also tell them, especially when at any time that I put a inside micrometer together, you always want to check the calibration with an outside micrometer. And we have different rods, show them how to change those. Read it the same. And again, this is showing the half-inch spacer, and I show that to them out in the lab. Various sizes. Company I work for, we actually measured 60 inches sometimes, although we had verniers also. Vernier caliper. Rockover technique. Okay, then depth micrometer. What I have here is how do you read it? We're going right to left instead of left to right. And again, we talk about the various parts, thimble. Again, I have enough of these and I'll pass them out. Every student will have one. Talk about the ratchet stop. I'll talk about how to change the rod right here. And again, I'll say make sure that this is tight. If it's not tight, you're going to get a false reading, so you want to check your calibration. Again, you want to make sure you're reading it the right way. Right to left, not left to right. Check calibration. This is using gauge blocks. I actually have a lecture later on. Next week you'll see my lecture in reference planes and gauge blocks. And then small hole gauges. We have various sets. I do have various parts out there that has a small hole. And the only way they're going to be able to give me that tolerance is by using these gauges, how to use those. And again, I'll say, is this a direct or indirect measurement? And again, it's an indirect measurement. They come in various sizes, ranges. For instance, this goes from a 1/8 to a 1/2 inch. As you adjust this, this actually just protrudes out and will just expand. transfer to go direct. And then good old telescopic gauge. In other words, you release this and it springs open, come in various ranges. And there are times when you have to use those also. I give an exam, as I said, in my final exam, I'll give them pictures of instruments. They have to identify them. I keep telling them that's not a T-wrench. Okay, I think before we move on, I'll see if there's any questions, but what I'm planning on doing, I still have some lecturing on gauge blocks, comparison measurement, and then I will end up, after all this lecture, I am going to show you some parts that we actually inspect and what do I look for. Like, are we looking for centerline distances? Are we looking for parallelism, outer roundness, whatever? And again, let me just go to that real quick and just show you what I'm planning on going with this. Angular measurement. There's my parts. So what I'm going to do is after we explain all the lecturing, is I'm going to show you these parts. What do I look for? How do they measure it, et cetera, so on and so forth. These are all the parts that I'm going to share with you. And again, you know, how we end up doing that. So that's where we're going to be heading, and I'll be doing that Tuesday. So we'll go ahead and finish the lecture on angular measurement, comparison measurement, attribute gauging, and measurement by control, gauge block consistency. That's where we're going to go next. And then we'll finish up with the dimensional metrology. I just share with you, when I first started teaching here, I've been teaching here since 1981. I graduated in 80 from here because of my industrial experience. I was an inspector, so that's where I got a lot of experience here with this. But I started teaching manufacturing processes, and again, I'd have people running engine lathes didn't know how to read a micrometer. Actually didn't know how to read a scale. And what I ended up doing is I was on an advisory board, and I said, we really need a dimensional metrology class and also incorporate some of that in this survey of manufacturing processes. They agreed. So we also offer a dimensional metrology class where they do a lot of measurement for 16 weeks in doing everything that I'm just talking about. And what you're getting here, I'm doing this in about 2 weeks. A lot of the measurement, they won't do everything that we measure, but what I'm looking for is consistency. You know, they know how to read a micrometer, they know how to read a micrometer over diameters, they know how to read a depth mic, and they know how to read a vernier caliper. So when they do their engine lathe work, which I'm going to share with you, some of the things we do out on the engine lathe and what we teach there, and then the mill, they will have the skill set needed to go ahead and hold the tolerance for the parts they're supposed to machine. Are there any questions? Okay, I think this is, as I said, it's a good place to stop. And we'll talk about the gauge blocks, comparison measurement, and then we'll talk about getting into centerline bore measurement. And again, we'll have some practice, and I will show you the various parts that we use for that.